The VCA seminar is by Professor Indranath Sengupta from IIT Gandhinagar. So the topics he will talk is some questions on bounds of Betti numbers for numerical semigroups. So I give it to Indranath for continuing his talk.
Thank you so much, Professor Patil, and very big thanks to Professor Jugal Verma for giving me this invitation, this chance to speak. And so when he asked me for a title and an abstract, then I was kind of not able to decide. And then I thought that, yeah, why not talk about this famous paper by Professor Kunz. The name of the paper you all probably know is The Value Semigroup of a One-Dimensional Gorenstein Ring, which appeared back in 1970. And I still find a big relevance of the paper, especially in the kind of work I do. And well, I didn't know at that time. I came to know about it later from one of the lectures by Professor Patil that Professor Kunz is no more. And so this is probably all the more reasons to pay tribute to him, pay tribute to his work. He has done some wonderful work all of us know as commutative algebraists. Okay, and I'll try to, so what my plan today is to first talk about this paper of Kunz, which talks about this, the value semigroup of a one-dimensional Gorenstein ring, and how the way he starts this paper is like this, that in a conversation about the paper or by the conversation about the thesis of Professor Jürgen Herzog, the name is Generators and Relations of Abelian Semigroups and Semigroup Rings. So all of us who have spent some time with semigroup rings, we all know about these Herzog's work and Kunz's work. So what Kunz says is that in a conversation about this Herzog's thesis, Oskar Zariski indicated that there should be a relation between Gorenstein rings and symmetric value semigroups, possibly allowing a new proof of a result of Herzog on complete intersections. So this is how this paper was written, possibly. That's what Professor Kunz indicates. So what I intend to do is that I would like to first present this paper by Professor Kunz. I still feel that it is very, very important because somewhere that the valuation theoretic approach is probably what one has to look again. And then towards the end, I will just present some observations on the bounds of Betti numbers. So which you may not find a direct link with Professor Kunz's paper, but I'll tell you why I have, how or what is the reason behind sort of tagging along this work of mine with my students with this Professor Kunz's paper. Okay, so since I'm going to write everything, so probably I'll be a little fast, and this is surely something which is very well known to the experts, but to the young graduate students, probably this is something new. So let me start. So this is the, I will be sort of shifting in between two windows. So this is, if you can see that in small letters, it's written Kunz over here. So this is the Kunz's paper, which I am going to discuss now. So the setup is the following. Oops. This for us is a local Noetherian reduced ring of dimension 1. I'll try to give the skeletons in this paper, the main skeleton of the proof as much as possible. QR is the total quotient ring. And you know the usual notations. Let me just still write it out, at least one. The integral closure of R in QR, and this denotes the M-adic completion. Of R. Okay, so now since we are going to talk about Gorenstein rings, and you know there are many equivalent definitions, so what for me, or rather as Kuhn says it, what we are going to take is the following, that R is Gorenstein if it satisfies one of the following equivalent conditions. One is that M contains, this is non-zero divisor for me, which generates an irreducible ideal. Two is that each principal ideal is irreducible. The third one is the length as an R module of this is 1, and anyway standard nevertheless. So this is, you all know this. And for each ideal A of R containing a non-zero divisor, the inverse is A. As usual, A inverse is taken in the total quotient ring. Okay, so now I guess I will, maybe I'll open it in 2 windows perhaps, if it helps. No, not that. Yeah. Okay, and then, you know, again, a standard definition is that, let me still set the notation, the ideal, we denote it by C, that is the annihilator of this R module, is called the conductor of R in R bar. Yes, yeah, I'll come to that. Yeah, correct. What Professor Verma suggested, a small change, that it should be a principal ideal. Yeah, so I'll come to that. So now this, you know, this is the largest ideal, which is both ideal in R and R bar, etc. Now this conductor plays the central role in Kunz's proof. So that is exactly what we are going to learn today. So you can, you know, for numerical semigroup rings, since this is going to be our primary object. So for example, you can take, if R is say t squared t cube, then you can see that this is going to be your ideal generated by square, or if you have TA, TB in general, where A, B are positive integers, GCDAB is 1, then the conductor ideal is TC, where C is exactly A minus B into B minus A minus 1 into, which is the conductor, since I have not yet defined yet, but those of you know what conductor is, then you would know immediately that this is the conductor of the numerical semigroup generated by A and B. Okay. Okay. Now a couple of definitions more, and then we will go to the main theorem. So now let me call them a few facts. Again, very standard ones. So one is that we will see that, okay, so let me write first. So if R bar is a finitely generated R module, in fact, you will see that this plays a very important role. Then the conductor ideal contains a non-zero divisor. And what is more important and what is really used in this proof is that if R is Gorenstein, then the length of this is 2D, where D is the length of the R module, R mod the conductor. Well, a way to see this is like if you have, say, let us say, if this is a maximal chain, of ideals in R, then what you do is you extend it to a D minus 2, or rather if I call it, yeah, I mean, it's all right, a D minus, no, a D minus 1 inverse, and then, and so on, all the way up to a 0 inverse, and that is C inverse, and that is R. And since this is going to be a maximal chain, in R bar, because you have the Gorenstein condition, and therefore you have the inverse. So therefore, this is a maximal chain. Since A inverse is A. That is by the Gorenstein condition on this. So, you know, this is kind of a very, very useful notion, because we will see that this actually connects the, when we are trying to understand that the ring R is Gorenstein if and only if the value semigroup is symmetric. So the symmetricity of the value semigroup would be in terms of the conductor of the semigroup, and that would connect to the conductor ideal of this ring R, okay, in order to show the Gorenstein property. Okay, so now so couple of definitions more. R is analytically unramified if the emedic completion is reduced and R is analytically irreducible if R cap is an integral domain. So these are the basic definitions we need. And so, you know, what the theorem is going to talk about, we will have is that we will assume that R is analytically reducible, and that would immediately give us, along with the fact that it's a one-dimensional reduced ring, etc., it will immediately give us that the integral closure R bar is going to be a discrete valuation ring. So basically, you can see that this analytically reducible is going to be, you can see this as a condition on R bar. And this discrete valuation ring is the valuation you will be working with. Then you will take the valuation semigroup. And this is how we will finally show that if you assume analytically reducibility, and then the Gorenstein property of R would be given by the symmetricity of the value semigroup. So this is what the main theorem is. But there is one more thing. Since I said at the beginning that this originated from Herzog's result, so obviously there was an attempt to sort of give a different proof, of course, in the local version, different proof of Herzog's observation. What was that observation? That for the numerical semigroup rings in embedding dimension 3, there are only two possible cases. One is that the defining ideal has 2 generators or 3 generators. So in that case, the Gorenstein and complete intersection, they are the same. They become equivalent. So now what could possibly make that happen is, this is the thing that we will be using while we finally prove Kunz's result and then see Herzog's results as a corollary. That is this observation by Serre, which says that let R be a Gorenstein ring such that the embedding dimension of R, I'm sure you know this, that is less than or equal to dimension of R plus 2, then R is a complete intersection. So you see, this is actually what is going to make it happen, that because this embedding dimension less than or equal to this bound, so in dimension 3, for this embedding dimension 3, we will see that the embedding dimension, you know what embedding dimension is, it is the mu of the maximal ideal, that minimal number of generators, or rather the k dimension of m mod m square over k, right? So therefore, this situation for embedding dimension 3 is really special, and that immediately follows from Kunz's result after, of course, we settle that. So let us now come to the main observation. But before that, what we need is what I said just now. So a couple of very important results. One is R is analytically unramified. Well, we don't directly need it, but let me at least mention this. If and only if R bar is a finitely generated R module. But we want more than that. So that is, R is analytically irreducible. You know, the definition is the embedded completion is an integral domain. But here you have the most important classification, the criteria, that R bar is a discrete valuation ring and a finitely generated R module. Okay, and there is an interesting result, I believe, by Cards, probably sometime around this, which says the following: the integral closure of an analytically unramified ring is local if and only if the ring is analytically reducible. So therefore, if you just look at this, then you definitely have lots of good things happening, that you have the discrete valuation ring property of, which is sort of the central most important thing, that you have the discrete valuation ring property of R bar. It's a finitely generated R module that anyway comes from analytically unramified itself. And also you have this fact that for an analytically unramified ring, the analytically reducibility comes from the local condition of the R bar. So basically, what the crux of the matter here is that, so here R bar is the ring which is sort of playing a very, very central role for analytical irreducibility. Okay, so now we are in a position to state Kunz's theorem. So R is analytically irreducible, makes it a DVR. So you know what that means. That means there is from this to Z for which R is the valuation ring. So this is the standard fact about this, essentially the definition of discrete valuation ring. And the value set or the value semigroup, and the value set is set of all, so let me call it VR, that is set of all Vx in Z, such that X is non-zero elements of R. Okay, and a few facts which kind of, you know, if you, so, you know, just for very young students, you know what valuation is. So basically you should, all the thing you have to remember is that this is a group homomorphism, and you have, whenever you have V of X plus Y, that's greater than or equal to minimum of Vx comma Vy. And of course you have Vxy is equal to Vx plus Vy. So that's it. And if you play with this, then you will see that, in fact, in Kunz's proof, you will see that the main things are basically coming from playing with the valuation again and again. There are many, many small facts which can be sort of listed down. But what is the first important thing is that this VR, this is of course contained in N. So by that I mean, and then you have 0 belonging to VR. Not hard to guess, right? Why 0 is coming. You have, this is the very important fact, is finite. And finally, VR is closed under addition. Okay, so this is exactly what you call a numerical semigroup, that it's a submonoid of the set of natural numbers, and it is finitely complemented. So that is the definition of a numerical semigroup. And incidentally, with the analytic irreducibility of a one-dimensional Noetherian local reduced ring, you have automatically a valuation coming into picture, and that valuation is giving rise to this valuation, the value set or the value semigroup. So we would be calling this VR the value semigroup. So let me call VR is the value semigroup. Okay, so now we should state the theorem first, and I will just make a small detour and say a few basic facts about numerical semigroups which we would require in proving Kunz's theorem. But let me state the theorem first. So the theorem, so this is the main theorem of the paper. It says that, let me state it as it is. Let R be a one-dimensional analytically irreducible Noetherian local ring. Now you will see this assumption which would happen in our situation very nicely, but which is, and let me write it first. Assume R and R bar have the same residue class field. I mean to say R mod M, basically. Okay, then R is Gorenstein. For example, if you are working over an algebraically closed field, suppose you assume that R mod M is algebraically closed, then this naturally happens. But in the context of these numerical semigroup rings, this is a very natural thing that happens, and therefore we really need not worry about it, but we will make a notice of the place where it is being used, okay, in the proof. So then R is Gorenstein if and only if the value semigroup is a symmetric numerical semigroup. So I'll just spend 5 minutes talking about this, and then I'll come back and then I'll prove this. Okay, so let me, yeah. Oops, just a minute, please. Okay. Okay, so this is some basic facts about numerical semigroup rings, because we will be spending the last few minutes talking about it. So let me just give you some very basic things, and which I'm probably all of you know. So first of all, so as usual, okay, so first definition is that a submonoid S of n is called a numerical semigroup if it is finitely complemented. Okay, so this is the definition, and by submonoid I mean that this contains 0 and this is closed under addition. That's it. Okay, in fact, maybe I give a couple of quick examples, and if it is something new to you, then you can just think over it for some time later on. So let me write 2 numerical semigroups and this onwards. So by this I mean 14 onwards, everything is there. So this is the subset of n that is going to be a numerical semigroup. This is one example. Another example is this one. Even integers inside n. Okay, so I just make a comment that S1 and S2 are, of course they are different, that is clear, but they are different because of the
Sorry, don't you want n minus s to be finite?
Yeah. Sorry. Thank you so much. Yeah. So I didn't mean to write that. Yeah. Sorry. Yeah. Thank you so much. Just a minute. I actually had something else in mind. So yeah. So for the time being, first let me say what I'm intending to say. So first thing is that, so this is not a numerical semigroup. This is just, you have the additivity, 0 belongs to this, but it is not finitely complemented, as Professor has pointed out, that this fact is not there. But what you see is that, so this complement set is infinite here, the complement set is finite here, but we will be able to give one more example. I'm just postponing it for some time because I'll come back to this and then I will give you the example where this, so let me call it S3. And here, if you see the numbers, so 14 onwards, everything is there, but from 0 to 13, you can see that the number of the elements which are there in the semigroup are precisely 0, 5, 7, 9, 10, 12, and of course the others are not there. Okay, and some other semigroup where this number is different. Okay, so there are precise terminologies, there are names by which we call them, but that is not what really what I intend to do. What I'm trying to say is that this gaps, the number of gaps in a numerical semigroup, I mean, forget about this example because this is not really numerical semigroup, but here you can see that this is not a numerical semigroup at all because the gap set is infinite. But what kind of role does the gap set play? So what is the gap set? That means those elements which are not there in the numerical semigroup. Okay, so here you see that number is something, whatever it is, and I'll be able to produce many more, in fact, which has different kind of gap sets. So this is exactly what is going to play a very central role, first about symmetricity and about something else, which I'll come towards the end. Okay, now, in fact, you can produce many such S3s. So theorem first is that every numerical semigroup, let me just use this shorthand. Every numerical semigroup has a unique minimal generating set. And a submonoid S of n is a numerical semigroup if and only if the GCD of elements is 1 and every non-trivial submonoid of n is isomorphic to a well, I don't really need it, but let me still make a mention. If I have time, I'll come to this also. Unique numerical semigroup. Not really required for my purpose. Okay. Now, a couple of things more. Now, this is, again, is a basic fact of this, that if S is a numerical semigroup, so remember, finitely complemented submonoid of n, then there exists an integer C in S such that C plus I belongs to S for every I, 0, 1, so on. And C minus 1 does not belong to S. So this is basically the most important thing about numerical semigroup is that from one number onwards, everything is here. And then the C is what is called the conductor of the numerical semigroup, and C minus 1 is what is called the Frobenius number of the numerical semigroup. You know that there is the Frobenius problem, which is another interesting problem. And now we are in a position to define that a numerical semigroup S is symmetric if the cardinality, so from C to Z, from C onwards, everything is there in the semigroup. So from 0 to C minus 1, you just count which are inside S and which are not in S, and their numbers match, and then you say that the semigroup is symmetric. Okay, and a quick fact is that S is symmetric if and only if the map from Z to Z given by X going to, so if you allow me to call it F, the Frobenius, F going to F minus X, this map maps S to N minus S and N minus S to S. So these are some these are the very basic facts which we need. We don't need anything more than this. We basically need the definition. So remember that this is your numerical semigroup, that from C everything is inside, and from 0 to C minus 1 you have the entries as well as the gap sets. The gaps, I mean some numbers are not there and some numbers are there and so on. So this is what you need. Okay, so let me now again go back to yeah. Okay, so this is what we are going to prove now, that if you have a one-dimensional, and this happens to be the most important assumption, as you can understand, because this is what gives me the fact that R bar is discrete valuation ring, and therefore you have the value semigroup, and you are connecting the Gorenstein property of R with the value semigroup of this, and then we will recover Herzog's result. Okay. Okay. So what are the main things? What are the main structures in this proof? Let me see what is the best I can do. No, I don't need this. Okay. So, yeah. Yeah, so the proof. Okay. So first of all, first fact is that, let me sort of put it under bullet. Okay. So the first fact is that what we can show, the conductor ideal, you remember this was annihilator of R bar over R. So basically R in R such that X R bar is contained, right? This is the conductor ideal. This, we can prove that this is basically all those elements in X is greater than or equal to C, where, so maybe I should have written it here itself, that, so let us assume that let C denote the conductor of VR. We have already mentioned that VR is a numerical semigroup ring, and you have heard me saying that this definitely has a number, everything onwards that belongs to the numerical semigroup. So let us call this as the conductor, and F is C minus 1, which is the Frobenius. Okay. Okay. So if you look at all these X in R bar such that Vx is greater than or equal to C, then this set is exactly the conductor ideal. Now, what is the main thing? Let me at least mention the main thing that you need in this, the main technique that you need. See, basically here, what the main technique that we need is the following, that we have assumed that R and R bar having the same residue field allows us to find a suitable unit E in R such that V of X minus ER is greater than Vx. So you can just keep this picture in mind, that you have this C, you have this. So I'll tell you in a minute what do I mean by this R. So you have Vx. So suppose, so one way is easy. You can easily show that the conductor ideal is actually contained in this. Now for the other way around, when you are, if you start with an X in R bar such that Vx is greater than or equal to C, that means, you know what, this is the conductor. Therefore, Vx is definitely in VR, right? Vx is in VR. So therefore, Vx is actually equal to VR for some R in R. But your X is in, so you have started with, for X in R bar, Vx is greater than or equal to C. So I'm starting with an element on the right hand side. And then since Vx is greater than or equal to C, therefore it is in the numerical semigroup VR. Therefore, I can write it as VR for some R in R. Now what I will do is that I will just do a sort of inductive step that you can choose a unit. Basically, you just keep on using your valuation V, and then this allows you to sort of jump this and come somewhere like this. And in this process, the second step would be that if C dash is the least V value, which of course exists, of the conductor ideal, C, then finally we can come to a state such that Vx minus R dash is greater than or equal to C dash for some R dash in R. Okay, so you just keep on doing this till you cross that C dash. But you know, this is a very basic fact about valuations. Once again, you just keep using V, and then you will see that the moment you have these elements, so let me write it, I think it's a lot easier. Yeah, let me put this bullet out here, that if Y is in R bar with the valuation being greater than or equal to the least value, and you know this is the least value appearing in the conductor ideal, the V value, then you have Y actually belongs to R. And from that it follows, therefore, X minus X dash is in R. Okay, so therefore X is in R. And now you can check easily that for some Y in R bar, V of XY, that is V of X plus V of Y, and that will be also greater than or equal to C. Okay, and then again by the same argument, your XY is in R, and that is what you exactly want, that this belongs to C. Okay, fine. So so this is the kind of, you will see more of this. So let me, I am just, I have to rush. So let me again show you the main point. So now let me come to this fact. So therefore, if you accept this, that the conductor ideal is nothing but this, that all those elements in R bar whose V value is at least C, and C being the conductor. Now let me go to the proof. So first part is that maybe, yeah, I write here itself. So suppose that the value semigroup is symmetric. And what do you want to show? You want to show that the ring is Gorenstein. And what is the Gorenstein we have? So what we are going to use is, yeah, so what we are going to use is this condition, that the length of this module is exactly equal to 1. Now, again, how do you do it? So what the main, let me write the main step here, and let me see if I can explain. Okay, so start with, in R, now if Vx belongs to Vr, again, similar argument, is equal to Vr for some R in R, and by a similar technique as above, you can actually get an R such that this is not in Vr. So therefore, you kind of throw away elements from R, and finally you make it happen that it is not in Vr for some R. I mean, just like what we did here, just something similar, that we can do the similar thing here. Now, how does it help? Okay, so maybe I'll just go back and, yeah. Okay, so if that is the case, then with your X in M inverse, and then you can, these simple checkings will tell you that this also belongs to M inverse, and then we may assume that Vx is not in Vr. Okay, and now what we want to show, that we now prove that this Vx has to be equal to n. And that would imply that the length, in fact, that would imply, let me write one more line. I'll then tell you the proof. So that would immediately imply that M inverse contains, apart from elements of R, only those elements which have Vx equal to n. Okay, and that eventually implies that this cannot be more than 1. Why? Because we will see that in between 0 and M inverse of R, we will not be, so this will stand out as a kind of composition series, because any element if you start with here in which is x, let us say x bar, says that x is not in R, and then you will be able to see that once you take the R span of that, because of this condition, you would immediately get this. Well, a little bit of a checking required, but this eventually proves that your length has to be 1. Now, how do you find that Vx equal to n? So once again, similar trick that if not, so I'm just trying to argue this, that if not, that means Vx must be less than n, right? Because Vx is not in VR, so greater than or equal to n is ruled out. So less than n, and then what you do is use n minus Vx, then that belongs to VR. Why? Because, so not n, sorry, mistake. F minus this, the Frobenius. So because VR is symmetric, we have assumed that VR is symmetric and we are proving that R is Gorenstein. So then this belongs to VR. And then again, you do the same thing. You write this F minus Vx as VR1 for some R1 in R. Okay. And, you know, from that, immediately what follows is that you will come to, after a few steps, you will come to a situation that X cannot belong to M inverse, which will be contradiction. Therefore, this is not possible. Therefore, this is possible. And eventually it comes that this is going to be a composition series for this R module, giving it the length to be nothing but 1. So this is how you, so basically, you are just playing with the valuation out here, nothing else. Let me show you the other way around, and then the last few minutes I will spend on, yeah. So the other part is that, so you are assuming that let R be Gorenstein, okay, and then the proof goes like this. So you want to show that VR is a symmetric numerical semigroup. Now, how you connect that? That is through the conductor ideal, right? That is exactly where this will play a role, the first observation. The proof goes like this. So suppose these are numbers in 0 to n. Oops, I'm making this mistake again and again. So 0 to f, the Frobenius, which are values of elements of R. Now what you do is the following. Let me just shorten the writing. So what you do is the following. You just consider these ideals okay, for I equal to 0, 1, and so on up to d minus 1. And then what you have is this chain. And in fact, this is a maximal chain. A maximal chain. That's very easy to see, because what you, if you just take any element in between, okay, so any element in between and with the valuation to be, let us say, suppose in between ai minus 1 and ai, with the valuation equal to vi minus 1, and then if you adjoin it to this ideal, you would get the full of ai. Okay, so therefore you cannot, it's going to be a proper containment. So that would immediately give you that the length is d, okay, but R is Gorenstein. So if you remember, this is what this is what we are going to use. This is what we are going to use, that right? Okay, so therefore I have so that means length is going to be 2D, and that immediately, and that is going to be my C. So once again, some facts which are being used, but they kind of follow very easily from the fact that are this from this valuation. So these are small checkings are required, like how do you prove that this is exactly equal to this, which essentially follows from this only. It's nothing very different. But then automatically what you are saying, since these were the elements, these D elements were the ones which are realized in VR, and there is, since here you are getting that the conductor is 2D, therefore obviously the number of elements which are not being realized is the same as the number of elements which are being realized up to the Frobenius, and therefore this VR is symmetric. Okay, so this is the theorem of Kuhn's, and let me quickly say in a couple of minutes that how does it follow. So what is that theorem which is proving now? It's not hard to guess. So this was the observation by Herzog that, so let me write it as a corollary, that let R be analytically irreducible Noetherian local ring of dimension 1, and suppose that the residue fields of R and R bar are the same, or you may assume that you're working over algebraically closed field, then R is, but you don't need this obviously, because for numerical semigroup rings this is going to happen, which you all know, and I'm going to say it in a minute. So then R is a complete intersection. Oh no, sorry, I need one more assumption, that suppose that the maximal ideal of M, maximal ideal M of R is 3 generated, then R is a complete intersection if and only if it is Gorenstein, if and only if, I mean, or maybe I write it, if and only if VR is symmetric. That means R is Gorenstein. So that's exactly, that was the main observation in Herzog's work. And now you can see why it follows, because of this, you have this, but you remember, this is what you have from, oops, let me take you there. Yeah, here. So this observation of Serre says that if the embedding dimension is at most dimension of R plus 2, in this case dimension is 1, and embedding dimension is definitely lesser than or equal to 3 because it's 3 generated, and therefore you have this complete intersection, and which nicely follows from Kunz's result. So this is the main this was the observation. So now another thing that I take from this observation is that, so if I just, so let me close this and let me take you to this. Yeah. So I'll come here. So this is the situation I have now. So you know that, give me a minute, please. Yeah, so suppose that S is a numerical semigroup. Minimally generated by, let me say, M0, M1 to ME minus 1. Okay, and assume that the GCD is 1. So you know that if you, it is also true that, so let me, maybe I just write the main thing that, so if you look at this parameterization, and call it phi, and P is the kernel, then this is your, what is called the semigroup ring. So this is my R, and this is sitting inside nicely in KT. You have the integral closure and this, and obviously this is your this. Okay, now so basically here's all. So this is with respect to, if you declare the weights of xi to be mi, then this is a nice graded K-algebra homomorphism. So you have a graded ideal, and this makes sense. And here you have mu p. Even you can take the instead of the algebraic case, you can just do it for polynomial ring, and same thing would nicely go through. And mu p is 2 or 3. So this was exactly Herzog's thesis, and based on which Kunz's theorem, which also proves in the fact that this is the situation when you have the Gorenstein and complete intersection, and this is the almost complete intersection. Now comes the question. So now this question happens to be much older. So the question is, if it probably dates back, if I'm not mistaken, that starting from Macaulay's answer back in 1916 to Avanker's proof with Macaulay's examples in 72, and then I will come to this stage, Mohs example, and another class of example by Brzezinski. So what is the example I am talking about? So my question is the following. Let me do it only from for the setting of this numerical semigroup ring. So that means numerical semigroup rings, by this I mean this object. Okay, and very nicely, if you see, if you are thinking of Kunz's theorem, if you are thinking of applying Kunz's theorem, that all your things are nicely set. You have a one-dimensional domain, and etc. And therefore you just need to see that when you have analytic irreducibility, the only thing you need to check is that when you have the say Gorenstein property, and that comes from the symmetricity of the numerical semigroup generated by M0 to ME minus 1. That's exactly what we know by Kunz. But then what kind of extension do we have of Herzog's results? That is the question. That given E greater than or equal to 3, is there an upper bound on the minimal number of generators of P? So this is the question now which can be asked, and which has turned out to be, answer is no. And the example, I believe the first example for this class for numerical semigroup rings was given by Brzezinski. So let me just quickly, I think my time is up. I'll just take a couple of minutes quickly. Is that fine? Okay, so so see, this this was Brzezinski's example. I think sometime around 75. So for him, E is 4, and the integers were, it was written in a slightly different way, but I will write it in a slightly different way. That is A into A plus 1. So this is M0. This is A plus 1 into A minus 1. This is A into A plus 1 plus A minus 1. And this is A into A minus 1. So these are the 4, and A is greater than or equal to 4 even integer. And he proves that mu p, so if I write it properly, then if for each A, if I say this is the defining ideal, for A greater than or equal to 4 even, this set is unbounded. Okay, so for E equal to 4, you do not have an upper bound, and this is a kind of apparently complicated, but this is a nice set of 4 integers for which it happens. Okay, now for the this also should be mentioned, Mohs examples, which are also very interesting. So this, he gives the example of, so space curves, characteristic zero field, n is an odd positive integer, m is n plus 1 by 2, lambda, I mean some technical, sorry, integer co-prime to m such that lambda is greater than n into n plus 1 into m. Now define, so this is not a monomial parametrization, but to kt as rho n of x is t to the power mn plus t to the power mn plus lambda, rho n of y is t to the power n plus 1 m, and rho n of z is t to the power n plus 2 m. Okay, and in this case, if you define Pn to be the kernel of rho n, then Pn, mu Pn needs at least 10 generators basically. So mu Pn is at least 10. Okay, and therefore once again unbounded. So here, for here you can see that for 3 it doesn't happen if it is a monomial parameterization, because that's Herzog's result, right? That is either 2 or 3. But for 3, if you want to give a situation in the case of power series, then you have to be careful about the analytic irreducibility. So because otherwise in the power series ring it may factorize, right? So therefore here, this is the example that he comes up with. Now I will just say a couple of things quickly. So question is here, if you see that this example, so if I want to give in the higher embedding dimension for E greater than or equal to 5, well, one way to do is that you just keep these numbers and treat the other variables as dummy. That is all right. But the point is, if I really want to, if the question is there a, so is there a kind of a general structure for constructing examples in arbitrary embedding dimension? So what I mean to say is that a numerical semigroup ring in arbitrary embedding dimension E, and then can you show that that has unbounded mu p? Okay. Now here, what you should be noticing is that, let me just rewrite Brzezinski's number once again. So the numbers are basically a into a minus 1. Unfortunately, the proof does not quite reveal that, but a careful reading, in fact, it does. So this is my, allow me to call it, say, alpha. This is alpha plus D. This is beta, and this is beta plus D. So this is basically, this D is the same, A minus 1. Okay, so what we propose is the following, what we call concatenation. So let A, B, D be positive integers. Consider the sequence and let us say A minus 1D, and then B, B plus D, and so on, B, 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 and minus 1D. Okay, so the embedding dimension is M plus N, and you assume that GCD of AD is 1, and also you assume that they generate the numerical semigroup minimally. Okay, so what you can see is that you have an arithmetic sequence out here. By the way, it's an interesting result by Professor Patil and Professor Balwant, that for arithmetic progressions, your mu p, etc., are all bounded. It's very nice. Okay, even the Cohen-Macaulay type, I mean the last Betti number, and so on and so forth. So what you are doing here is that, and which is quite interesting, that what you do is you just take two arithmetic sequences with the same common difference, and you just need to break that chain. Okay, so what you do is that also assume that this cannot be completed to an arithmetic sequence, which you can do by doing something like this: D does not divide B minus A. And what appears, at least that's what I could see with my students Joydeep and Ranjana, that for fairly large embedding dimensions, it really gives you the structure where you definitely have mu p is unbounded if A, B, D chosen carefully. And not just mu p, in fact, the last mu p is the first Betti number, even the last Betti number, and possibly all the Betti numbers. In fact, that's what we could see in the Brzezinski's example also, that possibly all the Betti numbers, they are all unbounded. Now, question is, we do not have a proof yet for the fact in general. Okay, so now why I am tagging it along with Kunz's result? See, this interesting fact is that if you read, this is also another work that we did with Ranjana and Joydeep, that we were trying to understand Mohs theorems, and what appears that Mohs proof actually uses, well, it doesn't, it's not a valuation, but what he calls it's what he calls a sigma weight, right? So he gives a weight, assign weights to each variable, and sort of it's kind of a that weight is playing a very important role to understand that which are the generators, or which kind of polynomials would be eventually, or which kind of power series would be eventually generating this prime ideal, and leading to an unbounded set of unbounded number. I mean that there is no upper bound on this number of generators of Pn. Okay, so and in our attempt to understand Mohs paper, what we saw is that in fact one can give a very nice algorithmic procedure also to understand these generators. One can compute the generators explicitly. Okay, and in fact it so happens that they have a determinator structure. So there are very interesting facts. So probably for this, or rather it's my question that probably a valuation theoretic technique, whether it can be again invoked for this kind of a statement, that what we are saying is that in general, if one chooses A, B, D carefully, then this kind of concatenation. So what is a concatenation? We have two arithmetic progressions with the same common difference, and you break the chain. So you do not let it fill it up. You cannot throw in more integers inside and then make it an arithmetic progression, or if you want to twist it further, you can in fact choose B somewhere here, okay, and make sure that it cannot be completed to an AP. Then you do have this situation which is like Brzezinski, or rather in general, which probably gives us a situation where we have a mu P is unbounded, and in fact all the Betti numbers, even if you calculate the pseudo-Frobenius number, that gives you the type, the the Cohen-Macaulay type, and also eventually the large Betti number. You have the unboundedness of everything, but we do not have a proof in general yet. We have only up to, let us say, 5, and we know what kind of family might work, but whether a technique like a valuation theoretic technique or a kind of a technique like Mo might work. So I think I'll stop here. Sorry for overshooting.
Anybody has any question or comments? Indranath, here in the last one, there has to be at least 1.
You mean here?
I mean,
Yes, absolutely. So in fact, to be on the safer side, we will say that M are at least, yes. In fact, it should be, yeah, I mean, let me mention what Professor Patil said. You mean N or M?
Either of them.
Yeah. So let me just say that both are bigger than or equal to 2, okay? Because anyway, we are looking for embedding dimension 4 and onwards, right? So therefore, yeah, absolutely correct. Yeah, we need at least this much. Otherwise, it will not be, because also your actually what I forgot to mention is that if you have only one of them, then also it is what you call the almost arithmetic sequence, and that again has been proved by Patil and Balwant Singh that you have all the nice boundedness happening. Yeah, so you need at least the correct length of these two. The length is your choice, but make sure that the common difference is the same and things like that. Yes.
Yes. Any more remarks or questions?
May I ask a question?
Sure.
Yes, please.
Yes. The final statement, you said that mu pay is unbounded, but for fixed A, B, and D, mu p is bounded because it is material. So
absolutely. Yeah. Okay. No, I'll just clarify. I'll take you back to this Brzezinski's example. So what it means to say is that if you change your A, where A is greater than or equal to 4 and even integer, then you get, for each A, you get a numerical semigroup, and you get a defining prime ideal, which we call PA, if you remember what the way I wrote here. Yeah. So PA, and if you collect these numbers, then there is no upper bound. So here what we are doing is that we are fixing the embedding dimension. So here the embedding dimension is E. You fix it, let us say for 5 or for 6. Then we are saying that if you choose your integers carefully like this, all you need to do is that you kind of take arithmetic sequences and put them side by side, but don't make them complete to one arithmetic sequence. Then for each of these parameters, you will be getting a PA, and those mu PAs will be unbounded.
I see. But then what do you mean by if A, B, D chosen carefully?
Yeah, what I mean, that's a very important question. Actually, there is, it is absolutely not true. In fact, this concatenation family shows very interesting behavior, that if you sort of change as was pointed out by Professor Patil, that your M and N, in fact, these M and N seem to play a very big role. I mean, of course, A, B, and D. So what I mean to say chosen carefully is that you need to choose these A, B, and D with respect to your M and N in such a way that you get the unbounded family, because you do have a possibility, you may even get a symmetric numerical semigroup. Okay, and in fact, you have a complete family for which mu p is bounded. So it is not true that every concatenation family will give you an unbounded mu p. But we have a class also, I mean, as a kind of a example, or rather we might say a conjecture, that I can tell you what are these A, B, and D in terms of M and N, for which unboundedness is probably true, but showing it computationally in the sense, the normal way to go about this numerical semigroups is to understand the Aperi set and things like that, or understand the Grosvenor basis. But you see, I mean, that's very, computationally very expensive. So probably one has to understand these numerical semigroups once again, and maybe through the valuation theoretic aspect, or maybe the kind of technique Mo has used in his paper.
And one more question.
Yes,
I have
please.
one more question. Is there any prospect to extend this theory to higher dimension, higher dimensional semigroup rings?
No, that so that's a very good question. In fact, I think that's one field which is still not much work has been done in terms of the number of generators. Probably it's possible to state, but I really have no idea how to go about it. Yes, of course, why not? I mean, like if you define, because let us say in N2, if we go to N2 and then ask a similar kind of questions, there are many questions which are absolutely wide open, and I really do not have much idea about it.
Thank you.
Any more questions or comments? What I was saying in the last question, what you had. Can you show me the last slides?
This one?
Here.
Yeah,
Perhaps it may be better to arrange these integers A and B so that this B is not in the semigroup generated by the earlier.
Yes, actually, see this, they should generate it minimally. First of all, that is required. Yeah. See this they should generate the numerical semigroup minimally. So that kind of takes care of that B should not be belonging to that. Yeah, that you need. Otherwise, it would sort of reduce and become a kind of a degenerate situation.
Okay. Okay, any more questions?
So I guess Professor Vijayalakshmi Trivedi, she wanted to say something. Ma'am, are you still at all?
Oh, that I had this trivial observation. Why there is a condition on GCD of the degree of those generators?
Well,
Because
I mean that
if it is numerical semigroup, then automatically the GCD has to be 1.
Right. So you might as well divide by the GCD and make them GCD 1, because
but otherwise it won't be numerical semigroup.
Yes,
right?
So in a sense, we are sort of trying to make a numerical semigroup, and since numerical semigroup condition is tagged with the GCD1 condition, so we sort of start with the generating set with the GCD1 condition. So that's the kind of the
Yeah,
usual.
but it's equivalent in some ways.
Yeah, but the point is, suppose you don't start with, then you still get that, because see, you need that. The GCD1 condition would eventually be required for your existence of the conductor, right? So if you do not have that, see the trouble is here. Say, for example, if you just have this simple enough just arithmetic progression, then your A plus D and so on, if A and D have some common divisor, then keep on, they will be there. So your GCD1 condition is not there. So eventually you have to divide by the GCD to make it a numerical semigroup, isn't it?
Yeah, no, I said you started with the assumption that it is a semigroup, numerical semigroup. Once you say it is a numerical semigroup, automatically it forces condition on GCD. That's what all I was saying.
Yeah, that's true. No, but the point is, here we started with the integers first.
No. I was looking not this definition.
Oh, the previous one? Oh, I see. Oh, acha. Maybe I kind of in a hurry. I just
not here.
Understood. I think here you were saying that.
Right.
Yeah. So I should have written this first and then come to this. You are right. Yeah. Sorry for the.
And
This.
yeah, hope to see have some progress on this problem. Yeah.
Yeah, thank you so much.
Yeah.
There is some progress, but the point is, I mean, one probably needs to, again, one is probably, it is essential to understand Kunz's proof once again in a better way.
Yeah. So are you trying some computer or something? No.
Well, it's a mixture of various things, because when we were trying with Mo's paper, and then it is definitely a mixture of two things when we are trying. But, just guessing results is not enough, because how do you prove this? Suppose you have candidates, how do you prove this? So that's why I said it's kind of not viable. So one has to, in fact, what is interesting is that in Mo's paper, what he defines as the he calls it the sigma weight. Okay, so what he does is he calls sigma x, sigma y, sigma z to be these are monomials in x, y, and z, and then he gives the elements which are the possible generators for Pn as those with sigma weight at least this much. Okay, so it's kind of a, these weights are going to play a role, and that is what helped us to give a precise method to, or rather precise steps to come up with the generators of Mo's ideals. So Mo does not really give the generators of the ideals. He gives that how to find these generators, in the sense that who could possibly be the generators, and then he is doing a counting, right? But so therefore we need to do something similar, perhaps. But again, any claim here is still not really substantiated. So I should be saying that it is just a guess. Yeah, but yes, there are sort of some mild evidences.
Okay.
But for E equal to 5, we have a complete proof that this family, the family which it's difficult to write it here, it gets a little complicated, but there is really, it is possible to give a very nice family for which mu p is really unbounded.
But you can write Betti numbers and everything?
No, I can't. I can write the last Betti number and the first Betti number, but not the intermediate ones. And both are unbounded.
Oh, okay.
Yeah, because the last Betti number can be calculated using the pseudo-Frobenius. So the Aperi set description actually helps us. But still, it's not easy, but still one can do it.
Okay, yeah. Thanks for a nice talk. Yeah.
Thank you so much.
Yeah.
All right, any more questions or remarks? If not, let us thank the speaker once again for his nice talk.
Thank you.
And with this, we will close today's session, and we will wait for the next announcement. Thank you.